Hello, my name is FAIZUL AMRI, and today I will be presenting my final year project with the title of the effect of different type of material for front car hood panel impact simulation. My supervisor name is Encik Wan Muhammad WARDI bin Wan Abdul Rahman. I'm from Department of Mechanical Engineering Technology, Faculty of Engineering Technology. The abstract for my research. In this research, an analysis was conducted on the topic of crash analysis. The objective is to analyze the total deformation and equivalent stress of the front car hood panel when collision happen at different velocity with different material. The analysis will be done by doing a simulation using ANSYS Workbench software. The software used for the simulation are SolidWorks, ANSYS Workbench, and Mechanical ADBL. Type of crash test for the crash analysis is frontal impact. The subject of analysis for the simulation are front car hood panel that been designed in SolidWorks, and fault fit support is a rigid wall. Three types of material will be subjected to the simulation model, which is structural steel, aluminum alloy, and AL6061TC. For the fit support, which is the rigid wall, concrete will be used as the general material. Whereas incoming speed were considered when the front car hood panel was simulated to crash into a wall. 5 theoretical velocity will be simulated in the simulation. The velocity are 20 km per hour, 40 km per hour, 60 km per hour, and 100 km per hour. It can be concluded from the simulation that structural steel has the highest total deformation and equilibrium stress than aluminum alloy and AL6061TC. The introduction for this research. Crash simulations are used by manufacturers during the computer-aided engineering (CAE) analysis of crashworthiness in the computer-aided design (CAD) process of modeling new vehicles. During a crash simulation, the kinetic energy or motion energy that a vehicle has before the impact is transformed into deformation energy, often by plastic deformation, which is plasticity at the end of the impact of the vehicle body material, body in white. Data gathered from the crash simulation demonstrate that the car body or railguard device is capable of shielding occupant of vehicle and even pedestrian hit by car from injury. The literature review done for this research. A crash test is a method of destructive testing that is typically done to ensure secure design quality and crashworthiness and crash reliability for various types of vehicle. Finite element analysis can generate realistic results that help scientists and engineers understand the way that cars are affected by different crash scenarios, and it is much more cost-effective to simulate car crash using a commercial software such as ANSYS. Vehicle crash is a highly nonlinear transient dynamic phenomenon. During an automobile crash, some parts will have plastic deformation and absorb a lot of energy. The crash analysis simulation and result can be used to assess both the crashworthiness of design chassis and to investigate ways to improve design and material. Next is the methodology for this simulation. Start, then we'll do literature review. After that, we will design CAD model of front car hood panel and rigid wall in SolidWorks. After that, we will assign material for the model. The material are structural steel and alloy AL6061T6. Then we will run simulation of frontal impact of the front car hood panel in ANSYS Workbench with the choice of the explicit dynamic for 5 different velocity: 20 km per hour, 40 km per hour, 60 km per hour, 80 km per hour, and 100 km per hour. From the explicit dynamic analysis, we will get two types of solution, which is equivalent stress analysis and total deformation analysis. From the solution, we will get the data collection. Then we will collect the data to get result and then analysis on the data. After that, there will be a discussion and conclusion and project. Result and discussion. There is two graphs for the result. This is the summary from the 5 velocity. The velocity is velocity, total deformation, and equivalent stress. First graph is the maximal total deformation of the front car hood panel for different material at different velocity. With the blue line is the structural steel, orange line is the aluminum alloy, and the gray line is for the material AL6061T6. At the y-axis is the maximum total deformation in meter unit. At the x-axis is the velocity for velocity with the unit of kilometer per hour. From the graph, we can see that the maximum total deformation happens at 100 km per hour. This is because deformation happen over time. The total deformation at 20 km per hour are the lowest among other total deformation at different velocity. Front car hood panel with structural steel material has the highest total deformation from aluminum alloy and AL6061T6. This can be seen on the graph. The difference of total deformation between structural steel and aluminum alloy are small compared to the total deformation between structural steel and AL6061T6. This may be related to the compressive yield strength of the material. The compressive yield strength of the structural steel is 2.5 exponent with the power of 8 Pascal, while for aluminum alloy is 2.8 exponent with the power of 8 Pascal, and this may cause the difference of total deformation between these two materials to be small, while compressive yield strength of AL6061T6 is 6.8 exponential with the power of 8 Pascal, and the big difference of these properties with structural steel makes AL6061T6 has much lower of total deformation. From this result, it showed that aluminum alloy has a good cross-potential while being lightweight. On this graph, the maximum okay, next. The second graph is the maximum equivalent stress on front car hood panel for different material at different velocity. From the table, we can see that maximum total deformation and the maximum equivalent stress at velocity of 100 km per hour has the highest value. These are caused by the force at the front car hood panel when it colliding with the rigid wall. From the data from table 15, it shows that the higher the velocity, the higher the force at the front car hood panel. Stress are increasing as the force increase. This can be shown in the equation of stress equal to force over area. The lowest value for the equivalent stress is at 20 km per hour. As the force for all three materials are the lowest at velocity, the difference of equivalent stress between the three materials also can be connected with the force when the front impact happens. The differentiality of the material will affect the mass of the front car hood panel. This data of density and mass can be seen in the technical paper for this research. Because of higher mass, the force also increase, which will also increase stress. This is shown in the technical paper that structural steel has higher mass and force, which will make it has higher equivalent stress for every velocity. The result pattern are followed by aluminum alloy, which has the second higher mass, and then followed by the structural steel. The maximum equivalent stress for structural steel at 100 km per hour is 1.664 exponential with the power of 9 Pascal. For aluminum alloy at velocity of 100 km per hour, the maximum equivalent stress is 5.881 exponential with the power of 8 Pascal. For AL6061T6 material, at the velocity of 100 km per hour, it has the maximum equivalent stress of 3.038 exponential with the power of 8 Pascal. The conclusion from this research: as for the conclusion, the objective of this simulation is to study the effect of different types of material for front car hood panel when subjected to frontal impact against rigid wall. Is considered successful. Material that has the highest total deformation is structural steel, followed by aluminum alloy and then Al6061T6. Structural steel has the highest equivalent stress. Aluminum alloy has the second highest equivalent stress, followed by Al6061T6 material. It can be concluded from this information that structural steel has the highest total deformation and equivalent stress than aluminum alloy and Al6061T6. The reference for this research are from Hiki A and Zhao S. Article from 2017 with the title of Finite Element Modeling and Simulation for of-car crash, and Lokhande, AP and Jaroka AG at 2016 with the title of Crash Analysis of Vehicle. Thank you for listening of this presentation.